Welcome back, AP Stats students. I'm going to try to make this brief for you all. So I'm going to be going over the answers to the part 2 of the review for our Unit 2 test. And hopefully this makes a little bit of sense to you. I'm going to keep it short and sweet. Number 1, the following is a scatter plot of the average final exam versus midterm scores for 11 sections of an introductory statistics class. Once you see average, I want you to think this is a compilation of every student that's in the room, and then we just compute it as one score. So this number right here is saying the average final exam score given the section's midterm average was, let's say, like a 30, between 39 and 40. And then what did they get overall as a class? So if this says average final exam, we should think averages are less scattered than all student data points. Now, if we put that together, it says the correlation coefficient of these data is R is equal to 0.829, or it's a pretty strong, more moderately strong to strong, positive linear association. Now it says this: if you had a scatter plot of the final exam score versus midterm score for all individual students, so instead of looking at the averages of each classes, there's 11 dots for 11 classes. What if instead we said we had 16 students in this class and 30 students in the other class and 45 students in section 4, 5, and 6? You can see we're going to have more data points. There's going to be more scatter when you have each individual score. Well, if there's more scatter, then you're going to have a lower R value. Or another way of thinking about this, the correlation will be weaker because averages make correlations stronger, or averages have higher correlation coefficients than relationships based on individual data. So the scatter plot for the final exam for students would show much more scatter and a weaker correlation. So that's number 1. Averages are more concentrated. Individual data points are more scattered. That's the point of that. Number 2, a plot of the residual versus the fitted values. Okay, so this is the residual plot for record-breaking times of female marathon runners. Based on this residual plot, does it seem reasonable to use a linear regression model? So what are we looking for? Is there a pattern? And it clearly looks like there is a line or a curve in our residuals. And since we see a clear pattern, then a least square regression line or a linear model does not seem appropriate. Remember, when we're looking at the residual plot from a linear model, we don't want to see anything. That's the whole goal. We don't want to see nothing. If you see a pattern, and now is it hard to determine a pattern from 1, 2, 3, 4, 5, 6 data points? Maybe not, but here it looks like there's a pattern. Number 3. Here's a scatter plot of weight versus height for students in an introductory stats class. The men are coded 1, so they're the dots, and the women are coded 2, which are the squares. Do we think there is a clear pattern? And if I was looking at just the squares, I can see there. If I was looking at, let's say, red, and this is where like colors is really helpful. So I'm just going to try to highlight the circles. If I try to find my circles, the circles kind of live more up here. Overall, it looks like a moderately strong positive association. Describe an association, think SODS. So a moderately strong positive association between weight and height of students. Now, the only other thing is we want to look like, is there anything else that we could describe going on here? And I want you to see that as we go further to the right, it looks more scattered, or the cloud overall, and let's use a third color, let's say pink. The cloud overall is getting more spread out. The taller the person are, the more fluctuation in the weight. Some people are lower, some people are way more. So we could say the variation in weight is larger. It's just, it's fluctuating more for larger heights. And now that is a better encapsulation of all of the data. Okay, part 2 says, comment on any differences you see between men and women. Now, I know we're bringing some of our previous knowledge, but this is where we look at the green versus the red. Green is girls, red is boys. So it appears from our scatter plot for introductory stats students, men on average, notice those are our squishy words, on average, appear to be taller and heavier than women. We can clearly see two groups, and there is a little overlap in this scatter plot. You can see that the green that we have, and then the red that we have, there's separation. Now, is there some overlap? Sure. But there are trends in each separate group. And do you think a linear model for the set of all data could accurately predict the weight of a student with the height of 70 inches? So first off, if we notice that these two groups can be separated, and there's a difference between men and women in the plot, it's most likely not correct. Correct to use a single linear model. Like, we should probably separate this between men and women. Furthermore, I want you to just look at, let's get rid of both of these just for a second, and let's look at orange. Here's 70. If I go 70, what do we notice about all of the values that I'm getting at a height of 70? Well, there's a lot of variation going on, and there's a lot of scatter. So there's a lot of change vertically at 70. We could estimate the weights of what's our lowest value here to our highest value here. The weights are varying by over 50 pounds for women, if we look at our women data, and our lowest male value to highest male value is almost a variation of 100. So furthermore, there appears to be large variation in weights at this height. Like, as we see that fluctuation, a model is not going to do a very good job in encapsulating that one X value, because we're getting a lot of spread in the weight for our students. Okay, moving on to part 2, chapter 10. So if you have a puppy who are feeding Hill's Science Diet, original puppy food, the feeding guidelines for puppies who are 10 to 12 months old are as follows. We're given the height, we're given the food, and we're given this scatter plot. So does it seem reasonable to perform a linear regression to predict the amount of food from a puppy's weight based on this data set? If this data was linear, then a line would be appropriate. Now, I want you to see that if I drew in this highlight, we're getting a curve. A slight curve, but a curve. In order to explicitly know if this was appropriate, we would like to see the residual plot. Now, they gave you the table so you could double check to see the residual. But clearly, we can see a bend in the scatter plot. And once you can see a bend, so a linear model is not appropriate. We're more likely going to re-express the data in order to use a linear regression. So we're going to need to use that linear model to see that bend, to straighten that curve out. Okay, we have one more question left. Obviously, you can check your answers below, and this is going to require us using a calculator. So let's look at the setup for this problem. So you're given the following costs to build a square deck for your house. Okay, square deck, outside house. Widths and costs. Use re-expressed data to create a model that predicts the costs of the deck based on the width. Okay, so I've went ahead just to save us some time and typed in our data values. So moving on to over the computer, what we want to look at is our scatter plot. Now we see that this scatter plot bends up. And I want you to think this is either moving up on the X or down on the Y, because it fits into our circle, our Tukey circle, in that third quadrant. So the other way to just double check to see if there's a pattern is we're going to go Menu, Analyze, first put on our regression model. We'll do A plus BX. The problem's telling us that it's going to need to be a re-expression. So we are also going to then look at our residual plot. Let's say show residual plot. Clearly there is a curve here in our residual plot, so a line is not appropriate. So if I move down the ladder, I could also take the square root of my cost function. So all I'm going to do is in that equals line, I'm going to type equals. I'm going to hit Control X squared to get the square root function, and then I'm going to type cost in. This is the half step below. And on your test, I'm going to tell you what you're supposed to do. So now if I switch back over, instead of cost, what I want is root cost. And we can see our data fits our line quite well. And we see our residual plot. Let's just turn that off and turn that on, just so we're definitely sure that this is showing the appropriateness. So Menu, Analyze, Regression, A plus BX. Menu, Analyze, Residual, Show residual plot. So when we change this over, we want to see no scatter. It was showing a different X value, so that's why it was showing 0. We obviously look at our residual plot and we see that there is no pattern. So switching back over to the notes, we want to write that model as an equation. So what we found is cost hat square root, since we took the square root of the y values, is equal to negative 0.135 plus 3.17 times our width. This moved down the ladder one step. So if you think the ladder was 1, then the next step below is 1/2. We could have also tried squaring the x, but this is the re-expression that we want to do. Why do we think the model is appropriate? Well, simply put, if we put our scatter plot and we have square root cost, like we saw, to our width, our data was much more linear, and our residual plot that we saw showed, let's say predicted cost, showed a lot more scatter. this is what we kind of had. There was no pattern to our residual plot, showing us that no pattern equals appropriate model. Okay, part C. Find the predicted cost of a square deck that is a width of 10.5 feet. So what we want is to plug in 10.5 into our function. So we have square root cost equals negative 0.135 plus 3.17 parentheses 10.5. Now I'm going to switch over to my calculator. And now on my calculator, I can just hit the button right under the escape and it gets me to my scratch pad. So what I have is negative 0.135 plus 3.17 parentheses 10.5. Enter. I get the square root of cost is equal to 33.15. But that's not actually how much it's going to cost me, because in order to solve for cost, I have to square that value. And if I do that, I'm just going to grab this answer, raise it to the second power, and my cost is $198.92. So since we always write out a sentence and we are not going to just leave our values as numerical, a deck with a width of 10.5 feet will cost approximately, squishy words, $1,098.92. Last question. Is it reasonable to use this model to predict the cost of a square deck that is 20 feet wide? Now notice, our model goes up to 15 feet in terms of width. 20 feet is significantly past 15. This is an idea about extrapolation. It's not reasonable to make a prediction for 20 feet, since 20 feet would be so because this is past our data set, and the previous question, 10.5, was inside our data set, 10.5 feet wide is appropriate, 20 feet is not appropriate. So I hope this video was helpful. I know it was short, sweet, and to the point. Go try some of the practice problems on Schoology, and you're going to be ready to go. See you in Unit 3, Falcons.